One of the more important applications in mechanics is of oscillations, simple harmonic oscillations and then extended types. But basically, any time that a force is proportional to the displacement, or in general, any phenomenon has a restoring effort proportional to how far it is from equilibrium, you get oscillations. And they very often look like simple harmonic oscillations, and that's what we're going to talk about next. A motion that repeats itself regularly is called periodic, and the time it takes for one exact repetition is called its period, usually symbolized by the letter capital T. Note the distinction between capital T and lowercase t. Lowercase t is the clock time, the time you're just reading as it just runs forward, but capital T is a specific thing, the period, the time to repeat once. The period of a day is 24 hours. The period of presidential elections in the United States is 4 years. Strictly speaking, for a phenomenon to be periodic, the period should be constant and should not itself change with time. But informally, we often relax this requirement. The period is the time for one repetition. A closely related concept is the frequency f, which is the number of cycles per time unit. In SI, the unit of frequency would be cycles per seconds, or seconds to the minus 1, since cycles is not a unit but only a counting trick. That's sort of unaesthetic, so we declare a new unit called the hertz, which is symbolized by capital H lowercase z, and we define it as 1 hertz is 1 cycle per second. Periodic motion is called simple harmonic motion if it's caused by a restoring force that is proportional to the deviation from equilibrium. The poster child for SHM is the motion of a mass attached to a spring. The force exerted by a spring has the magnitude F equals Ks, where S is the stretch in the spring, or when S is negative, a compression. This moves the mass back and forth past the equilibrium position. We pull the thing over from its equilibrium position, and it feels a force this way, so it starts to accelerate that way. But when it passes through the equilibrium position, the force reverses, and then it goes this way, and then bounces back and forth in an ideal situation forever. Graphs of simple harmonic motion. If you were to measure the position of a mass over a long time, you'd see it repeat. The graph of that position forms a particular curve, which is called a sinusoid. It looks like a sine or a cosine. Sinusoid is just a generic term for sine or cosine or some variant thereof. An older name for the sine and cosine functions were the harmonic functions, which is why this is called the simple harmonic motion. They were called that because this is also the motion associated with the tones that you hear in harmonies. Let's start our clock let's start our clock, which is t equals 0, at the moment the spring has been stretched and let go from rest. Call that position x equals a. In this case, the position x at any time t will follow a cosine curve. X is a cosine times this thing, 2 pi over the period times the clock time. This equation only works if you're in radian mode. That's what the 2 pi there is doing. The period of cosine is 2 pi. You could make this work by saying 360 degrees over t, but that's clunky and not really great for calculus reasons. So stick with radian mode and 2 pi. We've already met the period, which is the time for repetition. We can pick any point and the point 1 cycle later, but we must make sure that's an identical point. That is saying, if we go from here to the next value that has that, it's not identical because here the thing is decreasing, but here the cosine curve is increasing. So these are not the same point. We'd have to go all the way over to here and call that one period, which you can see is the same as all the other ones marked here. The maximum displacement from equilibrium is called its amplitude and is usually symbolized by capital A. Notice that A is the absolute value of the greatest distance from the equilibrium. It also turns out to be half the difference between the max and minimum values. And finally, note that the object oscillates back and forth between x equals a and x equals minus a. Although the motion is not constant, there are 4 important moments in any period. The motion goes from being at the amplitude to being at 0 to being at minus the amplitude to being at 0 to being back to the amplitude every quarter period. And they're spaced evenly, which is nice. That's about the only thing that's spaced evenly. The cosine curve is not otherwise very elegant and precise, but it happens to have a certain kind of symmetries at these locations, and they're worth knowing that you have a quarter t, a half t, 3/4 t, and t again, and then it repeats. Uniform circular motion and simple harmonic motion are intimately connected. In fact, simple harmonic motion is what results when you consider the projection of a uniform circular motion onto one axis. So consider a wheel of radius a rotating with an angular speed omega, which means that omega is delta theta over delta t, where theta is the angle swept out by a radius. Put a small bump on the edge of the wheel. The shadow of the bump will move along the ground according to simple harmonic motion. In other words, as the wheel goes around, as the bump goes around, the shadow part drifts down and is like this, going back and forth with a cosine. This reinforces, as we said earlier, that omega was 2 pi over t, and thus we usually write the expression not with 2 pi over t in it, but instead according to this cosine, that x is a cosine omega t. When talking about a rotating object, omega is the angular speed. When talking about simple harmonic motion, omega is the angular frequency. Both are actually the same thing, and you can use either term for omega. It really is the same thing. Here's an illustration of how they're connected. You can see that the vertical position of the spring at any time is the same as the vertical position of the ball at any time. So the spring is going back and forth with simple harmonic motion according to a cosine, as the ball goes around according to the same angular speed. Velocity in simple harmonic motion. We can extend this further and find the velocity of the shadow as well. By the way, I want to note that there's a real shortcut here. Of course, v is just dx dt. So if you've got in there in your calculus, it's d dt of a cosine omega t. The a comes outside, and we have d dt of cosine omega t. And then we do chain rule. So we have the a, we get minus the sine of omega t times the derivative of omega t, which is just omega. And you can see, hopefully relatively straightforwardly, that will end up being the same as this. Note that v equals 0 occurs when x equals plus or minus a, because that's when the object is turning around at its maximum extent. Also notice whatever v does, x does the same thing 1/4 period later. We say that the position lags the velocity by 1/4 period. Since the maximum value of sine is 1, we see that the maximum speed, Vmax, is a omega. This occurs at x equals 0, after which the object begins to either stretch or compress the spring, depending on its current direction. Similar reasoning lets us connect a to x, and we'll find that a is minus a omega squared cosine omega t, but then a cosine omega t is just x, and so we get just, minus omega squared x. Since f equals ma, we see that f is proportional to x, which is not unexpected since we actually started from that. The acceleration leads the position by 1/2 period, and its maximum value is a omega squared. It attains that value, but in opposite direction, at each end of the motion. A cart attached to a spring is displaced from equilibrium and then released. There is no friction. The arrows and signs above the cart here indicate the positive and negative directions for the position of the car. A graph of the displacement as a function of time for the car is shown, and we'll have a bunch of questions on the next page that we will choose from each of these as either a labeled point or no such point. When is the acceleration positive? Well, remember that the acceleration is omega squared or minus omega squared times x. So when x is positive, a is negative, and vice versa. So when is the acceleration positive? It's positive when the position is negative. So here to here and here to here. That's answer A. When is the net force on the cart equal to 0? Well, the net force will be 0 when the acceleration is 0, and the acceleration is 0 when x is 0, since they're proportional. So I'm really looking for when the position is 0, and that's easy because it's a position graph. So here, and here, and here, and here. When is the velocity 0, but the net force non-zero? Well, the velocity is 0, of course, whenever the tangent line is horizontal. And we see that because the position is non-zero there, the force is always non-zero when the velocity is 0. So that's when those are. When are the position, velocity, and acceleration simultaneously positive? Never. The acceleration and the position are of opposite sign, so they can't both be positive. And then finally, when is the velocity opposite in sign to the acceleration? So we need to have the velocity be positive, but the acceleration be negative, or vice versa. So the acceleration is positive in the blue regions, and we're going to want the velocity to be negative if the acceleration is positive. So we're looking at this part, and likewise here. The acceleration will be negative when the position is positive, and then we want the velocity to be positive. So something like here and here. And then here, just to sum up those results. I guess I should have pulled out the letter from here, and I did not, but we can go back to our screen and look, and they would be all these points here.